Okay, so the next question that we have is question number 3, and it says show that the following statement is true by the method of contrapositive. So you want to use the method of contrapositive to show that the following statement is true. So the method of contrapositive, basically you have if P then Q. If you want to use the method of contrapositive to show that basically this is true, to prove this to be true, you need to show that if not Q, then not P. If not Q, then not P. Okay? And I want to that is actually correct. And the statement is P if X is an integer. The statement is P if X belongs to the set of integers and X squared is even, then X is also even. X is even. So I can write this statement. So if X is an integer and X squared is even, then X is also even. So I write this statement as, for example, Q. I can basically break this down into X belongs to the set of integers and X squared is even, and R, basically X is even. Okay. Now what I need to do is basically I need to do this. I need to show that if not Q, then not P. I'm sorry. In this case, I have to show that. I have to show based on the letters that I have chosen here. If I call this R, I have to show if not R, then not Q. And R here basically refers to your then clause, and Q refers to your if clause, right? So what that means is that, okay, so if I want to show if not R, if I want to show R is not true, so not R would be some statement like, for example, X is odd. X is odd. Because your R is X is even, so the negation of that would be X is odd. So then what that means is that I can write X as, for example, some number like 2 and for example plus 1, where basically n is an integer. If n is an integer, so if X is equal to 2n plus 1, now X squared, so here we said that here this is my not R. Not R is X is odd, and that implies that X must be in the form of some form 2n plus 1, where n is an integer. So then what that means is that then x squared is equal to 2n plus 1 whole squared, which is equal to 4n squared, which is equal to 4n squared plus 1 plus 2 times basically 2n, which is equal to 4n, which is equal to 4n. So here what we want to show is not q, meaning that we want to show that q, basically q is x squared is even. So I want to show here that x squared is actually odd. So then I can write this as basically 4n squared plus n plus 1, which I can write as 4 times n squared plus n plus 1, which means that basically now this is an even number multiplied by this n, and this n is some integer, and this is the same thing as if you wrote, for example, 2 times n squared plus n plus 1. Whether you had a 2 or a 4 or a 6, it doesn't really matter. It has to be an even number. And then you add a 1 to it, and then you will get an odd number, right? So this implies that q is not true, which implies that not q basically is true, right? So what we have shown here now is that basically we have shown if not r, then not q, or basically this way, there is no if then. What we have shown is basically not r implies not q, which implies that p is true, that your statement p is true. So that's basically, for example, how you can solve this problem. Now let me go over the solution here and see what they have done to solve the problem. So what they have done is p is if x an integer and x squared is even, then x is also even. So the answer is p. If x is an integer and x squared is even, then x is also even. Q is basically that, and r is the next basically statement. To prove that p is true by contrapositive method, we assume that r is false, and then prove that q is also false. So that x is not even. To prove that q is false, it has to be proved that x is not an integer, or x squared is not even. Okay. So x is not even implies that x squared is also not even. Okay, therefore statement q is false. Okay, so they have not gone through the algebra, but basically they have done the exact same thing. So the next question that we have is question number 4, is by giving a counter example, show that the following statements are not true. So we want to use counter example. You want to use counter example to show that, to prove not true basically. prove false. So you want to use counterexample to show that the following statements are not true or they are false, basically. Now, number one is if all the angles of a triangle are equal, the statement is P. If all the angles of a triangle are equal, then the triangle is an obtuse angle triangle. Then the triangle is an obtuse angled triangle. Okay, so this one is a little bit, so let's see how we can actually solve it. Okay, so now in order to show show using the counterexample to prove that this statement, for example, is false, you have some basically if-then clause. This is your if, this is your then. So using counterexample, I can break down this statement as, for example, I can take this part as Q. I can take this part as Q, for example, and I can take this part as R, for example. And then using what I have here is now if Q, then R. So since I want to use counterexample, what I need to do is that I need to provide an example, a Q, that basically results in a not R, meaning that I have to show if Q then not R. And if I can show one such example, then that means that basically then this statement is simply false. So now if Q is, if I want to show if Q then R, that means that Q is true. So I have to assume that Q is true. Q being true basically implies that that basically means that all the angles in a triangle are equal. So that means that, so if I take one, basically if all the angles are equal, all the angles being equal, if I take the angle as x, for example, then basically x plus x plus x, then x plus x plus x is going to be equal to 180 degrees, because the sum of the internal angles of a triangle is 180 degrees. That means that x is equal to 60 degrees. So if x is equal to 60 degrees, that means that then every angle this is an acute angle, and so every angle is an acute angle, right? So if every angle is an acute angle in the triangle, then there is no obtuse angle in the triangle, meaning that R is false. So what we have shown is that if Q then not R, which means that basically P is false, using a counter example. Now let me see how they have done it here in the book, number 4, part 1. If all the angles of a triangle are equal, then the angle is an obtuse angle. So the given statement is of the form: if Q then R. So Q, all the angles of the triangle are equal. R, the triangle is an obtuse angle triangle. The given statement P has to be proved false. For this purpose, it has to be proved that if Q then not R, which is basically what we have written over here. This has to be proved. This has to be proved. And to show this, angles of a triangle are required such that none of them is an obtuse angle. It is known that the sum of all the angles of a triangle is 180 degrees. Therefore, if all the 3 angles are equal, then each of them is of measure 60 degrees, which what we showed here, which is not an obtuse angle. In an equilateral triangle, the measure of all the angles is equal. However, the triangle is an obtuse angle triangle, is not an obtuse angle triangle. Thus, it can be concluded that the given statement P is false. So that's basically, for example, how you do this one over here. Or the next one is basically we have another statement Q. We have another statement Q which says that the equation x squared minus 1, equation x squared minus 1 is equal to 0, does not have a root lying between 0 and 2. Does not have a root lying between 0 and 2. So this equation is x squared minus 1 is equal to 0. So that is x squared is equal to 1, which means that x is equal to plus or minus 1. So there is actually one of the roots of this equation is actually between 0 and 2, which is basically positive 1. Now, and of course this is a counter example. Now, in order to basically show that logically, what I need to do, because sometimes you make sense of an statement basically in a wrong way, meaning that, for example, so for example, if you want to write this example in an if-then form, so writing Q in if-then form, what I need to do is basically your if clause would be, so your Q would be basically if, for example, you have the equation, if you have the equation, for example, x squared minus 1 is equal to 0, then, for example, then the roots don't lie between 0 and 2. Okay, so that's the if-then form of this statement. Now, what you want to do, again, you want to, now basically your statement is in the form if for example, if S and R, let's call these, for example, S and R. Let's call this S, and let's call this part, for example, R. So now your statement is in the form if S, then R, So what that means is that now you have to, in order to provide the counter example, or in order to prove this wrong, you have to show that basically if S, then not R. Okay? If S, then not R. So when I say if S, what that means is that S is true. So if S is true, that means that you can write basically x squared minus 1 is equal to 0, and then x squared is equal to positive 1, and then x is equal to plus or minus 1, which means that R is, which means that R is false. Because positive 1 is actually between 0 and 2. Therefore we have shown that if S, then not R, which proves Q basically false, which proves Q false. So that is that. Now question number 5 is, which of the following statements are true and which are false? In each case give a valid reason for saying so. So now we have 5 statements. We have to know whether they are true or false. So, well, mathematics is basically built in such a way that you have first, I mean, based on my understanding, I'm not really sure if what I'm saying is actually right. It must be right based on what I have seen. Mathematics is, well, again, as far as I know, is made based on the, I mean, when it comes to these logical statements, first you need to kind of make sure that, or at least guess that the statement is true or it's false, and then prove it. It's not like you can start by the proof and then find out whether the statement is true or false. Usually you don't do it that way. Usually you know whether something is true or false, and then you have to prove it. You have to prove that the statement is either true or false. That's basically how you do it. So now in such cases you need to take a look at the statement and kind of at least guess whether the statement is true or false, and then prove the same. Okay. So, for example, let's say that you have this. There is the part 1 of this question. There is a statement P, which says each radius of a circle is a chord of a circle. Now there is of course this is false. I know that because I can provide a counter example, meaning that if I had some circle over here, and if I drew a circle, select border 1 pixel, and if I had this circle over here, the chord is basically any line that connects any point of the circumference to any other point of the circumference. In fact, that is actually by definition wrong. Meaning that if I have this radius, for example, I mean no radius is actually a chord of the circle, because the chord of the circle has to touch 2 points on the circumference of the circle, but there is no radius that touches 2 points on the circumference of the circle. Any radius that you draw here, it will just simply go through one of the points is the center, and the other point is going to be some point on the circumference. So this is absolutely wrong. So, and the same reason has been given here. It says that according to the definition of chord, it should intersect the circle at 2 distinct points, which is of course never the case here. So the statement here is false. It is of course false. Number 2, basically statement Q is the center of a circle bisects each chord of the circle. The center of a circle bisects each chord of the circle. Each chord of the circle. So it says that the center of a circle bisects each chord of the circle. Now if you have a circle over here and this is the center, now a chord is basically there are some chords that do not pass through the center of the circle. For example, this chord over here or this chord over here. But there is actually, for example, this chord that does bisect, that is actually bisected by the center of the circle. So these are all counter examples to show that basically that is not, this statement is false. So and here it says again the same thing. The given statement is false if the chord is not the diameter of the circle, which is basically this case here. If the chord is not the diameter, then the center will not bisect the chord. In other words, the center of the circle only bisects the diameter, which is the chord of the circle, which is the chord of the circle. So that's basically the reason that you can provide that. Or as another example, circle is a particular case of an ellipse. Yes, that's true, I suppose, because if you in an ellipse you have well, I have forgotten what an ellipse actually is. An ellipse is basically something like this, and you have something like this, and suppose that of course these are another part of the ellipse, and then once you have this ellipse you have two foci that are that are a certain distance away from the center of the ellipse. Now I have forgotten the exact things about the exact particulars of an ellipse. There is this distance over here that is called A, for example. There is this distance over here that is called B or C or something else. But if basically this distance, is equal to this distance, if these two distances are the same, then basically the ellipse becomes a circle. And the equation of an ellipse is basically x squared over a squared plus y squared over plus y squared. Of course, I cannot get into ellipses right now. Y squared over b squared is equal to 1, and the equation of a circle is x squared over and if you put a and b equal to 1, if you put a is equal to b is equal to 1, you will get basically x squared plus y squared is equal to 1, which is a circle. So you can say that circle is a particular case of an ellipse. Thus this statement is true. I did a whole chapter on ellipses and circles and everything, probably even on YouTube here, but well, you forget them really. You cannot remember them. I mean, it's not. There are a few of these. There is the circle, there is the ellipse, there is the parabola, there is the hyperbola, there is I think 4 of them. And then each of them you have to know basically the equation, how they behave, and so on and so forth. But well, you forget them. You have to, if you want to basically remember, then you have to go back and read them a little bit. But well, the statement is true. Statement S is if x and y are integers such that x is greater than y, then negative x is less than negative y. So if x and y belong to the set of integers such that x is greater than y, then of course negative x is less than negative y. And this is true because, for example, suppose that x and y are integers. Suppose that, for example, this is 0, x is greater than y. Suppose that x is this is x and this is y. I'm sorry, the other way around. Let's say that x is greater than y, so this is x and this is y. Then, of course, negative x would be way over here, and negative y would be over here. And so, of course, negative x is less than negative y. That is true. And they have used the rule of inequality, meaning that they have written basically x is greater than y, and then if you multiply this by a negative 1, you get negative x is less than negative y. Multiply by a negative 1, greater than becomes less than, and so negative x is less than negative y. Much better than the way that I solved the problem. I mean, you're actually supposed to do it this way, not using, probably a number line would be also valid, but this is what I would, of course, prefer. And basically statement T is the square root of 11 is a rational number, which is false. We can prove that it is false. We have proved that for square root of 7, we can prove it in the same way for square root of 11. And the reason is that it's a prime number. So 11 is a prime number, and we know that the square root of any prime number is an irrational number. Therefore, the square root of 11 is an irrational number, thus the given statement is false. So you can of course use the same way that we proved that the square root of 7 was, for example, the square root of 7 was irrational, to prove that this is also irrational. But then you wouldn't have proved it for every prime number. Then you would have to find some way to prove it for all prime numbers, probably using the method of mathematical induction or something like that. That would be interesting, but I don't really see the need to do it right now. Now, in the next example, or in the next video, we will talk about miscellaneous examples. There is a couple of them here and not much, and then we have a couple more exercises. There is not much left here, so we will take care of them in the next videos. I'll see you in the next video.